Good day everyone, welcome back to the channel. In today's video we are going to talk about permissions within our Linux terminal course. Unix based operating systems diverge from Microsoft DOS based ones by being both multitasking and multi-user systems. What does this signify? It implies that multiple individuals can operate the computer simultaneously despite typically having just one keyboard and monitor. Multiple users can access it. For instance, if a computer is connected to a network or the internet, remote users can log in through SSH, which is also known as secure shell, and use the computer. Moreover, remote users can run graphical applications and view the graphical output on a remote display. The X window system accommodates this within its fundamental structure. Linux's ability to support multiple users isn't a recent novelty. It's intricately woven into the operating system's design. This design choice aligns with the era when Unix emerged. Back then, computers weren't personal, they were sizable, costly, and centralized. University computer systems, for instance, had a main central computer in one building and terminals scattered across the campus, all linked to their central unit. Consequently, these computers accommodated numerous users concurrently. To ensure practicality, a system had to be created to safeguard users from each other. It was crucial to prevent one user's action from crashing the computer or meddling with the files of another user. In this chapter, our focus will be on examining this fundamental aspect of system security and presenting the subsequent commands. ID: display user's identity. Chmod: change a file's mode. Unmask: set the default file permissions. Su: run a shell as another user. Sudo: execute a command as another user. chown: change file's owner. chgrp: change a file's group ownership. And passwd: change a user's password. Owners, group members, and everybody else. During our exploration of the system in chapter 3, we might have faced an issue while attempting to inspect a file like /etc/shadow. So for example, we'll say file /etc/shadow. So over here, as we can see, we don't have read permission. And if we try less /etc/shadow, it says permission denied. This error occurs because as regular users, we lack the permission to read this file. Within the Unix security framework, users possess ownership of files and directories, thereby controlling their accessibility. Users can also be part of a group, enabling multiple users. Access is permitted by the owners. Furthermore, an owner can grant specific access rights to everyone, known in Unix as the world. To retrieve details about your identity, utilize the id command. So if we type the id command, we get the following details. So consider the output. When user accounts are generated, users receive a numerical designation referred to as a user id or uid, which is then translated into a username for human readability. Additionally, users are allocated a primary group ID or GID and can be part of supplementary groups. The provided example is from a Fedora system. However, on alternate systems like Ubuntu, the output might appear slightly distinct. As you can see, as we're using Pop OS, which is based on Ubuntu, this is the output that we got on the Ubuntu system. All right.
Unlock the world of Daisy Ninja puzzle books, where excitement meets brain power. Dive into the mind-bending labyrinths of Maze Mastermind. Conquer the Sudoku challenges in Sudoku Ultimate, uncover hidden words in Word Search Wizard, and decode mysteries in Word Spy Adventures. Whether you're soaring above the clouds or speeding down the tracks, turn your downtime into brain-boosting fun. Perfect for all ages, these books guarantee hours of entertainment. Daisy Ninja Puzzle Books, your passport to endless excitement on the go. New release each month.
Which is similar to this output. Okay. The disparity in UID and GID numbers arise because Fedora initiates its numbering from regular user accounts at 500, whereas Ubuntu commences at 1000. Moreover, the Ubuntu user is affiliated with a greater number of groups, influenced by Ubuntu's method of administering privileges for system devices and services. This information stems from a couple of text files, as is often the case in Linux. User accounts find definition in the /etc/passwd file, while groups are outlined in the /etc/group file. As user accounts and groups are established, these files undergo modifications alongside the /etc/shadow, a file that stores password related details within the /etc/passwd file. Each user account specifies the login name, UID and GID, the account's actual name, home directory, and the login shell. Examining the contents of /etc/passwd and /etc/group reveals not only regular users accounts but entries for super users, UID 0, and various other system users. In the upcoming chapter on processes, you'll discover that some of these additional users are notably active, while numerous Unix-like systems allocate regular users to a shareable group like users. Contemporary Linux methodology involves establishing an exclusive solitary member group bearing the user's name. This simplifies certain permission allocation procedures. Reading, writing, and executing file and directory access privileges are delineated through read, write, and execute permissions. Examining the output of the ls command provides insight into how this is executed. So let's have a look. So if we say foo.txt and then we'll say ls-l foo.txt, and then we'll see all the details. The initial 10 characters within the listing denote the file attributes, with the first character representing the file type. These are the common file types you will typically encounter, although there are rarer types as well. Dash means a regular file, a D means it's a directory, L a symbolic link. Notice that with symbolic links, the remaining file attributes are always RW, XRW, XRW, X, and dummy values. The real file attributes are those of the file the symbolic link points to. C, a character special file. This file type refers to a device that handles data as a stream of bytes, such as terminal or a modem. B, a block special file. This file type refers to a device that handles data in blocks, such as a hard drive or a CD-ROM drive. The subsequent 9 characters within the file attributes, known as the file mode, signify the read, write, and execute authorization for the file's owner, the group owner, and all other users. So owner is the first 3, group is the middle 3, and the world is the following 3. When set, the RWX mode attributes having the following effects on the file and directories. So R allows a file to be opened, and read allows a directory's contents to be listed if the execute attributes is also set. W allows a file to be written to or truncated. However, this attribute does not allow files to be renamed or deleted. The ability to delete or rename file is determined by directory attributes. In directories, W allows files within a directory to be created, deleted, or renamed if the execute attribute is also set. X allows a file to be treated as a program and executed. Program files written in scripting languages must also be set as readable to be executed. Directories allows a directory to be entered. Example, CD directory. Here are some examples of the file attribute settings. -rw followed by 6 dashes, a standard file that grants read, write, and execute permissions solely to the file's owner with no access permitted for anybody else. -rw followed by 7 dashes, a typical file that allows read and write permissions exclusively for the file's owner with no access granted to anyone else. -rw, -r, ~r, and ~, a standard file that permits read and write privileges solely for the file's owner, allows members of the file's owner group to read the file and is accessible to everyone. -rwxr -xr -x, a typical file granting read, write, and execute permissions exclusively to the file's owner while allowing everyone else to read and execute it. Now -rw followed by 4 dashes, a standard file allowing read and write access solely to the file's owner and members of the file's group owner. LRWX RWXRWX, a symbolic link, possesses placeholder permissions known as dummy permissions. A symbolic link possesses placeholder permissions known as dummy permissions, while the actual permissions are retained by the file indicated by the symbolic link. DRWXRWX followed by 3 dashes, a directory that allows the owner and the members of the owner group to enter, create, rename, and delete files within. And finally, DRWXR-X followed by 3 dashes, a directory where the owner has permission to access, create, rename, and delete files within. Members of the owner group can access the directory but lack the ability to create, delete, or rename files within. Now let's talk about chmod, which changes file mode. To modify the mode permissions of a file or directory, the chmod command is utilized. It's important to note that only the file's owner or the super user can alter the mode of a file or directory. Chmod provides 2 methods for specifying mode changes: octal number representation and symbolic representation. Let's begin by exploring octal number representation. Do note what on earth is an octal. Octal base 8 and its counterpart hexadecimal base 16 represent number systems frequently utilized in computer language. Human counting generally operates in base 10 due to our 10 fingers. However, computers having only 1 finger utilizing binary base 2 with just 2 numerals 0 and 1. Binary counting progresses like this: 0 1 1 0 1 1 1 0 0 and so on. In octal counting involves 0 through 7: 0 1 2 3 4 5 6 7, 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 7, 2 0 2 1 and so on. Hexadecimal utilizes 0 through 9 and adds the letter A through F, so that is 0 1 2 3 up till 9, then A B C D E F, then 1 0 1 1 1 2 1 3 and so on. While binary suits computers due to its binary nature, what purpose do octals and hexadecimal serve? The answer lies in human convenience. Often computers represent small data portions as bit patterns. Consider on RGB color. A pixel typically consists of 8 bits, each of red, green, and blue. Reading and writing long binary numbers daily isn't ideal. This is where octal and hexadecimal come in. Each hexadecimal digit represents 4 binary digits, while in octal, each digit signifies 3 binary digits. For instance, a 24-digit binary for a medium blue color is this number, can be condensed into a 6-digit hexadecimal number like this. Here each component red, green, blue align with their respective bits. So this is red, this is green, and this is blue. Although hexadecimal notion is more prevalent now, octal's ability to express 3 binary bits remain useful. Using octal notions involve employing octal numbers to establish the desired permission pattern. Given that each digit in an octal number denotes 3 binary digits, this aligns neatly with the file mode storage scheme. The following table illustrates this concept. So 0 octal is 3 zeros in binary or 3 dashes, 1 is 001 or dash dash X, 2 in octal is 010 or dash W dash, 3 is 011 dash W X, 4 is 100, that is R dash dash, 5 is 101, that is R dash X, 6 is 110, that is R W dash, and 7 is 111, which is RWX. Using 3 octal digits allows us to configure the file mode for the owner, group owner, and everyone else. So let's look at this. So we'll say foo.txt, then we'll say ls-l foo.text. We have seen this output as previously observed. Now we can say chmod 600 foo.text. Now let's look at the ls-l output. And as you can see, it has been changed like this. With the argument 600, we adjusted the permissions for the owner to read and write, excluding all permissions for the group owners and others. While recalling the octal to binary mapping might appear cumbersome, you'll typically work with a few common ones, which is 7, that is RWX, 6 RW dash, 5 R dash X, 4 R dash dash, and 0, which is 3 dashes. Chmod also incorporates a symbolic representation for defining file modes. Symbolic notion consists of 3 segments identifying the target, indicating the operation, and specifying the permission to be set. To denote who is impacted, a blend of characters such as U, G, O, and A, it is utilized in the following manner. So the symbol U, short for user, but means the file or directory owner. G, that is group owner. O, short for others, but means world. A, short for all, the combination of U, G, and O. When no character is specified, it defaults to all, that is A. The operation can be represented by a plus symbol to add a permission, a dash to remove a permission, or an equal sign to apply only the specified permissions while removing all others. Permissions are indicated using the R, W, and X characters. Below are a few instances of symbolic notations. These are the notations and their meanings. U plus X, add execute permissions for the owner. U dash X, remove execute permissions from the owner. Plus X, add execute permissions for the owner, group, or world, equivalent to A plus X. O dash RW, remove the read and write permissions from anyone besides the owner and the group owner. Go equals RW, set the group owner and anyone besides the owner to have read and write permissions. If either the group owner or world previously had execute permissions, they are removed. U plus X and G equals RX, add execute permissions for the owner and set the permissions for the group and others to read and execute. Multiple specifications may be separated by comma. While some individuals favor octal notion, others strongly prefer symbolic notion. Symbolic notion holds the advantage of enabling you to adjust a single attribute without affecting the others. Refer to the chmod manual page for comprehensive information and a rundown of available operations. Regarding the dash recursive note of caution, it applies changes to both files and directories, which might not always be ideal, as files and directories often require different permissions. Setting file mode with the GUI. Now that we have observed the process of setting permissions for files and directories, we can gain a clearer comprehension of the permission dialogues within the graphical user interface or the GUI. In Nautilus, GNOME, or Conqueror in KDE, accessing the properties dialog by right-clicking on a file or the directory icon provides an insight. Below is an example from KDE 3.5. So we are using GNOME, and to access the permissions, we have our file explorer open. So we'll right click on the file and then click properties, and in the permissions tab we get all the permissions that are given to this file. So we can change them from read only to read and write. We can change the group, we can change the access, and then we can change the access for others, and then if it's an executable you can check this box, and so on. In this view, the configuration for the owner, group, and worlds are displayed in KDE. Accessing the advanced permissions button opens a secondary dialog enabling individual adjustments for each mode, as I showed you in GNOME. Another triumph for comprehension facilitated through the command line. Now let's talk about the unmask command, which sets default permissions. The unmask command manages the default permissions assigned to a newly created file. It employs octal notation to signify a mask of bits that should be removed from a file's mode attributes. Let's delve into this. Okay, so first of all, we'll remove the foo.text, and then we'll say umask. Then we'll create foo.text. Now let's say ls-l foo.text, and you'll see the following output. Let's have a look. Initially, we eliminated any existing copy of foo.text to ensure a clean start. Subsequently, running the umask command without an argument displayed the current value indicating 0002. Alternatively, 0022 is another commonly used default value representing the octal representation of our mask. Following this, we generated a fresh instance of the file foo.txt and examine its permission. The owner and the group possesses both read and write permissions, whereas everyone else is granted only read permission. The absence of write permissions for others is due to the mask value. Let's redo our demonstration. This time, configure the mask manually. So to achieve that, we'll remove the foo.txt first, then we'll say umask 0000, and we'll create foo.txt, and then we'll finally say ls-l foo.txt, and as you can see, the permissions are now different from the previous permissions. Like here, these permissions were like this, and now they're like this. Okay, when we disable the mask by setting it to 0000, effectively turning it off, the file becomes world writable. Exploring this process requires revisiting octal numbers. By converting the mask into binary and comparing it with the attributes, we gain insight into the changes occurring. Okay, so original file mode was --rw-rw-rw-rw- mask 000 000 000 010. The result was --rw-rw-r-. Okay, so for now, disregard the leading zeros. We'll address those shortly. And notice that where 1 appears in our mask, like over here, it removes an attribute. In this instance, the world's write permission. That's the function of the mask. Whenever a 1 appears in the binary representation of the mask, it unsets an attribute. If we examine a mask value of 0022, we can discern its impact. So the original file mode is --rw-rw-rw-rw- mask would be 000 000 010 and 010. The result would be --rw-r- and r-. Okay, once more, whenever 1 is present in the binary representation, it conceals out the respective attributes. Experiment with different values. Consider using some 7s to become familiar with this process. Once finished, ensure to tidy up. Once you're done practicing, you may just remove the foo.txt file and then set the umask to 000 and 2. Okay, usually you won't need to alter the mask. The default provided by your distribution will suffice. Yet in certain high security scenarios, you may need to manage it yourself. Some special permissions, although we often encounter an actual permission mask as a 3-digit number, technically it's more accurate to express it in 4 digits. Why? Apart from read, write, and execute permissions, there are additional less utilized settings. The first is the set UID bit octal 4000. When applied to an executable file, it changes the effective user ID from the real user to that of the program's owner, typically granted to select programs owned by the superuser. It allows an ordinary user running a setuid root program to access files and directory, restricted for regular users. Given its security implications, the number of setuid programs should be minimized. The second less used setting in the setgid bit octal 2000, which like setuid alt is the effective group ID. When set on a directory, newly created files within inherit the directory's group ownership rather than that of the file's creator. This proves beneficial in shared directories where a common group requires access to all files irrespective of the owner's primary group. The third is the sticky bit octal 1000, legacy from ancient Unix that designated an executable file as not swappable. Though Linux disregards this on files, applying it to directory prevents users from deleting or renaming files unless they are the directory owner, file owner, or the superuser. It's often used in directories like /temp to regulate file access. Using chmod with symbolic notions, you can set these special permissions. For instance, assigning setuid to a program, chmod u plus s program, setting set gid to a directory, chmod g plus s dir, or applying the sticky bit to a directory, chmod plus t dir. When using ls, you can identify special permissions in the output. A set uid program -rw sr-xr-x, a directory with the set gid attributes drwxr wsr-x, a directory with the sticky bit set drwxr-wxr-wt. Changing identities. Occasionally, we might need to assume the identity of a user or another user. This is commonly sought to acquire superuser privileges for administrative tasks. However, it's also feasible to become another regular user, useful for tasks like account testing. There are 3 methods to adopt an alternative identity: log out and log back in as the alternate user, use the su command, and use the sudo command. We'll pass over the initial method as it's less convenient compared to the other 2 options. Within our current shell, the su command facilitates assuming another user's identity. It allows the launch of a new shell session using users' IDs or executing a single command as that user. On the other hand, the sudo command enables an administrator to configure a file /etc/sudoers, defining specific commands that certain users can execute under an assumed identity. The selection between these commands typically depends on the Linux distribution. Although your distribution may incorporate both commands, its setup will likely favor one over the other. Let's begin with su. Su, run a shell with substitute user and group IDs. The su command initiates a shell as a different user. The command's syntax appear as follows: su-l, then the user. When -l option is added, the resulting shell session becomes a login session for designated user. This action involves loading the user's environment and switching the working directory to the user's home directory, which is typically the desired behavior. If no user is specified, it defaults to the superuser. Interestingly, the -l option can be abbreviated as dash, which is more common usage. To launch a shell for the superuser, the command would appear as this. So all you have to do is enter su dash, then your password, then you will be logged into the root account. Upon executing the command, a prompt for user's password appears. Upon successful authentication, a new shell prompt emerges, denoting super user privileges indicated by the hash symbol instead of the $sign. So this $sign would change to a hash if you become a super user, and the current working directory shifts to the super user's home directory, usually /root. Inside this, new shell commands can be executed with super user privileges. To revert to the previous shell, simply input exit. Okay, so once you're done, you can simply type exit and you'll be back to your own account. You can execute a single command without any initializing a new interactive session by using the su in this manner: su-c and then the command. In this format, a solitary command line is transferred to the new shell for execution. It's crucial to encase the command within quotes to prevent expansion in our current shell and ensure it happens within the new shell. So you'll say su-c and then the single quotes ls-l, then /root/star and your root password. Then you'll see the following output. Okay, I'm not able to show you these outputs on my system because I don't have the root access. So now let's talk about sudo. Execute a command as another user. The sudo command, akin to su in many aspects, offers significant additional functionalities. An administrator can set up sudo to enable an ordinary user to execute commands as a distinct user, often the super user, in a highly controlled manner. Specifically, user might be limited to one or more specific commands while being restricted from executing others. Another notable distinction is that sudo usage doesn't necessitate the superuser's password. Instead, the user employs their own password for authentication. For instance, suppose sudo is configured to permit the execution of a hypothetical backup program named backup_script, which demands superuser privileges. Using sudo, it can be accomplished as follows. So this is a dummy scenario. So for example, if the program was called backup script, we'll say sudo, then the name of the script, then your password, then it'll start executing that particular command. Upon entering the command, we are prompted for a password, not superuser's password. Once the authentication is successful, the specified command is executed. An important contrast between the su and sudo lies is sudo's operation. It doesn't initiate a new shell or load another user's environment. Consequently, commands do not require any different coding compared to when sudo is not in use. However, this behavior can be altered by specifying different options. Refer to the sudo man page for comprehensive detail. To see what privileges are granted by sudo, use the -l option to list them. So you can just say sudo -l your password, and these are the privileges that are provided on the system to the sudo user. Ubuntu and sudo. One persistent issue for regular users involve executing tasks that demand superuser privileges, such as software installations, system configuration modifications, and device access. In the Windows environment, users often acquire administrative privileges, enabling them to perform these tasks. However, this also grants the same abilities to programs executed by the user, paving the way for potential malware like viruses to exploit the system freely. In the Unix realm, owing to its multi-user legacy, there's a clearer distinction between regular users and administrators. The Unix approach involves granting superuser privileges only when necessary, commonly facilitated by the su and the sudo commands. In the past, most Linux distributions relied on su for this purpose, as it doesn't demand the configuration required by the sudo, and having a root account aligns with Unix tradition. However, this led to a problem. Users often operated unnecessarily as root, seeking to avoid permission-denied messages. Unfortunately, this significantly reduced the security of Linux system compared to Windows system. A risky practice. Ubuntu, upon its introduction, pursued a different approach. By default, Ubuntu prohibits login to the root account by not setting a password for the account and instead utilizing sudo to confer superuser privileges. The initial user account receives full access to superuser privileges via sudo and can grant similar powers to subsequent user accounts. So as I mentioned, this is an Ubuntu based system called Pop OS. It does not allow access to the root user. Okay, now let's talk about chown, change file owner and group. The chown command facilitates altering the owner and group owner of a file or directory. Using this command necessitates superuser privileges. The syntax for chown or chown appears as follows: chown owner and the group and the file. Chown has the capability to modify either the file owner, the file group owner, or both based on the initial arguments provided in the command. Below are a few examples. The argument and the results. The Bob changes the ownership of the file from its current owner to the user Bob. Bob then users changes the ownership to the file from its current owner to user Bob and changes the file group owner to group users. Admins changes the group owner to the group admins. The file owner is unchanged. Bob then the changes the file owner from the current owner to user Bob and changes the group owner to the login group of user Bob. Consider a scenario involving two users, Janet, who possesses superuser privileges, and Tony, who does not. Janet aims to replicate a file from her home directory into Tony's home directory. To grant Tony the ability to edit the file, Janet modifies the ownership of the copied file, transitioning it from Janet to Tony. So that would look like this. Janet would say sudo cp myfile.txt, then the home directory of Tony. She'll enter her password. Then she'll say sudo ls-l Tony slash myfile.txt, and these would be the permissions of that file. And she'll say sudo chown Tony, then the directory of the file. Then she'll say sudo ls-l Tony my file, and the read and write permissions of the file would be displayed. Okay, in this instance, the user Janet duplicates the file from her directory to the user Tony's home directory. Subsequently, Janet alters the ownership of the file from root, which occurred due to the user use of sudo, to Tony, employing the trailing colon within the initial argument. Janet also adjusts the group ownership of the file to Tony's login group, identified as the Tony group. After the initial use of sudo, Janet wasn't prompt for her password. This behavior occurs because sudo is most configurable in most configurations, maintains a level of trust for several minutes until its time expires. chgrp changed group ownership. In earlier Unix versions, the chown command exclusively modified the ownership and not the group ownership. To manage group ownership, a distinct command named chgrp was employed. Its functionality resembled chown but was more restricted in scope. Now let's talk about exercising our privileges. Now that we have grasped the mechanics of permissions, let's put this knowledge into action. We'll illustrate the resolution to a frequent dilemma. Establishing a shared directory. Picture two users named Bill and Karen. Both possess music CD collections and aim to create a shared directory. This space will serve as a repository for their music file in OGG or BIS or MP3 format. User Bill holds super user privileges accessible by sudo. Initially, a group must be formed that includes both Bill and Karen as participants. Utilizing the graphical user management tool, Bill establishes a group named music and include users Bill and Karen as its members. So next, Bill creates the directory for the music files. He'll say sudo make dir, then he'll create the directory inside the shared folder. As Bill is managing files outside his home directory, he needs super user privileges. Upon creating the directory, it assumes the following ownership and permissions: ls-ld/user/local/share/music, and these are the privileges. From the observation, the directory is owned by the root and holds 755 permissions. To enable sharing of this directory, Bill must modify the group ownership and the group permissions to permit writing. So he'll say sudo chown then :user/local/share/music, sudo chmod 775/user/local/share/music, then ls-ld/user/local/share/music, and these are the change permissions. This setup signifies that we have established a directory /user/local/share/music possessed by root and permitting read and write access for the group music. Group music comprises Bill and Karen as members, granting them the capability to create files within the /user/local/share music directory. While other users can view the directory's content, they lack the permission to generate files within it. However, there remains an issue. Under the existing permissions, any files and directories generated within the music directory will inherit the standard permission of users Bill and Karen. So if you're logged in as Bill and create a file in this particular directory, which is in the shared music directory, then you'll say ls-l of the shared music directory. You'll see the following output. There are actually two concerns here. Initially, the default umask on this system is 0022, hindering group members from writing file attributes to other group members. While this wouldn't be an issue if the shared directory solely housed files, it's problematic since this directory will contain music typically arranged in artists and album hierarchies. Group members require the capability to create files and directories within directories establishing by fellow members. To address this, we need to modify the umask employed by Bill and Karen to 0002. Instead, another issue arises where each file and directory generated by a user defaults to their primary group rather than the group music. To resolve this setting, the set gid bit on the directory can rectify this matter. So you change it like this. You'll say sudo chmod g+s and then the path to the directory. Then when you check the permissions, they will look like this. Let's verify if the updated permissions resolve the issue. We'll adjust this umask to 0002, eliminates the earlier test file and generates a new test file and directory. So we'll say umask 0002 rm, then he'll remove the test file, then he'll create the new test file, then he'll create a new test directory. Then when he checks the permission of the music directory, he can see the following permissions. Okay, now both files and directories are produced with the appropriate permissions, enabling all group music members to generate files and directories within the music directory. The persisting concern lies with the umask, as the required setting remains effective only until the session concludes and necessitate a reset. In chapter 11, we'll explore methods to establishing a lasting adjustment to the umask command. Okay, changing your password. We'll conclude this chapter by addressing the procedure for setting passwords for yourself or other users. If you possess super user privileges to establish or modify a password, the passwd command is employed. The command's syntax appears as follows. That's passwd, then the name of the user. To alter your password, simply execute the passwd command. You'll receive prompt for both your old password and the new password. Okay, so I'll show you how that works. Is passwd. So now it is asking for me to enter my current password. Once I enter the current password of my current account, which is dev, it'll ask me for my new Unix password or the new password for this system. But because we are not changing the password in my system, we are not going to go through this. But if you are interested, you can continue forward with this command. Okay, the passwd command aims to implement the use of strong passwords. As a result, it will reject passwords that are too brief, closely resemble prior passwords, consists of dictionary words, or are easily predictable. So once you enter your new password, it will check is that if it's too similar to the old one, or it is way too short, or it is based on a dictionary word. Okay, so you'll have to be careful of what kind of password you are using. Okay, with super user privileges, you can designate a username as an argument to the passwd command, allowing the alteration of passwords for the users. Additional options are accessible to the super user, facilitating account locking, password expiration, and more. For detailed information, refer to the passwd man page. Now let's summarize the chapter. Throughout this chapter, we have explored how Unix-like systems like Linux oversee user permissions, permit read, write, and execution, access to file and directories. The fundamental concept of this permission structure trace back to the inception of Unix and have endured quite effectively over time. However, the innate permission system in Unix-like systems lacks the intricate granularity found in more contemporary systems. Alright guys, so I'll end the chapter here. Do go through all the commands that I have not showed. I want you to practice them yourself, and in the meantime, have a good one, and I will see you in the next video. Take care. Bye bye.